Okay, so we're going to talk about what's called the cross product or the vector product, which I forgot to mention. The dot product is also called the scalar product. It's called a scalar product because when you do it, you get into it with the scalar. As the name implies, when you do the cross product, you get a vector. It's more complicated, and I'm just going to explain. Graphically, it's kind of difficult to explain, and they actually just do it kind of a little using this thumb thing. So the rules relative to the value, is it negative or positive? The direction is also interesting. So anyway, let's just do it. So the vector product is important for, I'm going to sneeze again, is important for calculating torques, which is force acting through a distance causing things to rotate around an axis. Again, we're going to have we can do this in 3 dimensions. So I think I will just keep this as 3 dimensions. So you're going to start with the vector that has 3 components in the 3 Cartesian directions. So this is vector A, this is vector B, okay, so those are my vector. To represent the operation of vector product is you use an X. And again, when you're dealing with numbers, 3 times 2 is 6. Okay, it doesn't 3 times 2 is 6. They basically mean the same thing when you're dealing with scalars, with numbers. Whereas for vectors, they're very different. So what is this? Well, let's just write it down. The answer is that when you have a scalar product of 2 vectors, it's equal to the magnitude of vector A times the magnitude of vector B times the sine of the angle between the 2. Now the direction, so this gives you a number, a magnitude, a value. The direction is perpendicular to the other 2 vectors in 3-dimensional space. So you always have to involve 3 dimensions when you do a cross product. And it's very difficult to draw something in 3 dimensions. So we're going to do it in 2 dimensions and then talk about it. So let's say we have vector A going like this, and I'm going to start off with them perpendicular to each other. They don't have to be perpendicular to each other. So this is vector A. This is vector B, going perpendicular to it. So this ends up, when you do a cross product, you actually end up with a vector. And depending upon whether this is going up or down, positive X or positive Y or negative Y direction, the vector is actually going either into or out of the plane of the board or of the screen. So the vector would point from, probably in this case, would point from the screen out towards you as a 3rd dimension. Now, if this vector A is going like this, it's still perpendicular to these 2 vectors, because these 2 vectors are still in the 2-dimensional plane of the screen, and the 3rd dimension is in and out of the screen. So it would still, the resultant, the vector, direction of the vector, this cross product, this vector product, is either going to be going in or out. It's still going to be going in. What this angle does, this is the angle, is as this angle between these 2 vectors gets smaller, the magnitude of the resulting cross product is smaller. So if you have 2 vectors that are perpendicular to each other, you can get the maximum cross product because the angle here would be 90 degrees. The sine of 90 degrees is 1. Whereas if you have the two vectors in the same direction, the cross product is 0. The direction is still, you have a direction, but you don't have any magnitude. Sine of 0, the area between these two is 0, is going to be sine of 0 is 0. So you get it 0 because this is 0, not because of the magnitude. So as you take a vector and you change the direction towards the direction of the vector, the cross product magnitude gets smaller. The direction is always perpendicular to this. So if I had a vector pointing up and I had a vector going out the screen, the cross product would be in this direction. So that's the basic concept of the direction. The direction depends, this direction of the vector depends upon using this rule. If you look in your book on page 22, if you take, I think you take your hand and put it in the direction of vector A, and then you curl your hand to the direction of vector B, and your thumb is going to point in the direction of the resultant vector associated with this cross product. Now the actual calculation of this requires you to do it, to be a little familiar with matrices, and I'm not sure if you guys have had matrices. It's just a shortcut way of doing it. There's also, if you look in the book on page 23, you'll see 123 gives you the long, drawn-out explanation. But I'm going to show you the shorter way to remember how to get the value of the actual magnitude of the cross product. So what I'm going to say is the magnitude, so I'm going to use vertical lines, the value, magnitude of the, and actually this gives you both magnitude and direction, so actually we don't have to put the magnitude here. Is represented in this way, A cross B. So we use a determinant to kind of give you the right way to calculate this thing. So you have the I direction in row 1, column 1. You have the J unit vector in the first row, second column, and you have the K unit vector here. The next row is taken up by the first vector in the cross product. So in this case, A is the first one. The Y component is the second, and the Z component is the third. And then the second vector in the cross product, or vector product, is B sub X, B sub Y, B sub Z. Now, if you've taken matrices, the determinant of these 9 elements, the way it works is you take this, the I vector, and you multiply it by the determinant of this submatrix. So that's what you do is you take A sub Y times B sub Z minus, so when you go this way and then you go that way. And when you go this way, you make it negative. So that's going to be A sub Z times B sub Y. So these are magnitudes that you're multiplying. So this will give you magnitude. This will give you the direction. Now the J, because it's in this position, and you'll learn all this if you take linear algebra. This position, you use the negative sign. So it becomes negative J hat. Negative J hat. You take a horizontal line through this element and you take a vertical line, and what that leaves is these 4 elements. And then you do the determinant of this small matrix that involves 4 terms. So you get A sub X times B sub Z minus these 2, which is A sub Z times B sub X. And then finally, this element, it becomes positive. And then you cross this row out and this column out, and you get this submatrix or subdeterminant. So you get A sub X times B sub Y. Again, those are values, magnitudes. So then you subtract the other direction, which is A sub y times b sub x. And that's the resulting vector with both all the magnitudes and all the directions correct. Notice if I had a two-dimensional matrix, I mean two-dimensional vector, so I have a sub x. A is a sub x times I plus a sub y times k, times j plus 0 times k, so there's no k component. And the b vector is equal to b sub x times I plus b sub y times j plus 0k. So I could just ignore those. I just put those in to show that it's a two-dimensional matrix. What would happen is that, a sub y, a sub z, and b sub z are 0. So this is 0, and this is 0, and this is 0, and this is 0. So those two terms cancel out completely. So all that's left when you do the cross product of those two vectors is the third term. So all you have is k hat times a sub x, b sub y minus a sub y, b sub x. So the cross product, magnitude-wise, is this times this minus that times that. And the other thing is that it's in the k direction, which is perpendicular. The k direction is the z direction, which in 3 dimensions, you draw a 3-dimensional looking graph. Typically you have, this is x, and this is y, and this is z. Or you might have, they're 3 mutually perpendicular. So that the angle here is 90 degrees, the angle here is 90 degrees, and the angle here is 90 degrees in 3 dimensions. And so if you have something in this plane, the xy plane, of two vectors that are cross product, the resultant vector is going to be in the z direction, in the one that's perpendicular. So that is how it works.